no way this worked ever. Why do people send me projects that don't even work? I don't understand how this is no way this could have worked on your computer. You know, like how? Alexander, how? Hey, what's up guys, my name is Cherno. Welcome back to the Code Review series, a series in which I review your exceptionally and increasingly suspicious projects. Last time, we used a VM. This time, we're using this new computer. The reason why is because a lot of these projects that people send me require, you know, GPU access, like direct kind of Vulkan access. As far as I'm aware, that's not that easy to set up inside a VM, or at least what I've tried so far. So I thought that I would sacrifice a computer for your benefit. You're welcome. So here we go. An honest attempt by Viker's Bike. Hello Cherno, my name is Alexander. Alexander? I thought it was Viker's Bike. 28 years old, from Sweden. I recently discovered your ray tracing series, which got me interested in starting my journey with Vulkan and ray tracing. The project is about 7+ months old as I stopped developing it, but what made me so unsure about the whole project was the way I structured it and how I wrapped everything around. Roast the code, fry the code, do whatever you want with it. I don't know, we'll see. I mean, maybe like a light poaching will be in order, but we'll figure it out. Here's the link, which I will have for you guys in the description below in case you want to check it out. And PS, the repo uses CMake and can build with either Linux or Windows. Excellent. Pretty good start. Last time I reviewed an actual game engine kind of project and you guys really seem to enjoy that. So I thought that like a Vulkan ray tracing engine might also be interesting. That's why we picked this guy here. So Ruby is an open source ray tracing engine made in modern C++ with Vulkan requirements, Vulkan SDK version 1.3, CMake, and Clang or MSVC build tools. I won't be adding support to macOS, but with enough tinkering, I'm sure you can get it to work on macOS. I actually don't know if any of the ray tracing, the hardware accelerated ray tracing stuff in Vulkan would work on macOS, just because macOS, to use Vulkan on macOS, you need to use Molten VK, which is like a layer that translates it into metal. I don't know if that supports any of the kind of ray tracing stuff like Vulkan 1.3, maybe Molten VK only supports like Vulkan 1.2. Oh, 3 weeks ago, completes Vulkan 1.3 support. Well, if Reddit's anything to go by, apparently you can. All right, anyway, let's get this started. Also, Ruby takes advantage of the dynamic rendering feature, which is interesting because I haven't personally used that in any of my projects, but it's kind of like a new-ish Vulkan feature that just greatly simplifies how verbose you need to set up like your pipelines, your render passes, and all of that stuff. And it makes it a lot easier if you have a smaller engine, I guess, or just a small project and you don't really need that level of depth. Now, as always, if you want me to review your project, then you can send it into chernoreview@gmail.com. That email address and some instructions will be in the description below. However, another thing you should be doing is using CodeRabbit, the sponsor of this video, to review your code. CodeRabbit is an AI-driven automatic code reviewer that gives you really great contextual feedback no matter what language you're using. It integrates really nicely with GitHub or GitLab and scans your pull requests in real time, highlighting potential bugs, security issues, or just giving you general suggestions on how to improve your code. Now, recently they released a Visual Studio Code plugin that you can use to code review your code before you actually commit it to GitHub or GitLab, which I think is a great feature. In fact, why don't we just try it out and see what it says about all the changes I ended up making as part of this code review. So here's future me after the code review. Let's have a look at what CodeRabbit says about the changes I made. So once you've installed the extension, you'll see this in VS Code. If we click on CodeRabbit, we can have a look at all of our files to review. So this is the code that we haven't yet committed to Git. And then we can just press review uncommitted changes. And it's just gonna start an automatic code review over all the changes that have happened to this repository. Now, depending of course on the size of your project and your usage, this can be completely free to run. And you can see that now that the review is completed, it tells us that it's basically got kind of 3 notes for us in 3 separate files, but also over here under this comments section, you can see that it has correctly recognized the fact that we fixed a critical bug with the view matrix accessor. Now, this is a little bit of a spoiler for the rest of this video, so I'm not going to go too deep into this. So there's that critical bug fix. Then we've also got some notes. So we might want to consider encapsulation implications of exposing member variables. This, of course, I just did for debug reasons. It's nice that it's pointed this out because a lot of the time you might just forget that you exposed something, you made it public just because you were debugging or trying to figure out the state of certain variables, and then you just commit it because you forget about it. So it's good that it points it out and also gives you a lot of really good information, which is why I think CodeRabbit is really good for beginners or people learning, because it doesn't just point out things that you might want to consider, it also explains them to you, which I think is really great. And then also in the render data.cc, see, it gives some comments about my little camera debug UI implementation, which is of course to come later in this video. It's well focused, providing a simple interface to modify the camera position, but it also suggests that we add some more things such as rotation with your pitch, because that's the way that rotation is actually defined inside the camera class. So overall, it's done a great job. Everything that is pointed out is pretty reasonable. And to be honest, it's pretty much what I would expect if you actually got a human to review your code, right? This isn't checking like all of the code in the code base to try and be like, oh, this might be a bug or that might be a bug. It's more or less if someone was to actually review your code like a human, what would they maybe suggest you do? And stuff like this, I think, is pretty reasonable. CodeRabbit is completely free for open source projects, or you can try it out for your private projects with a 14-day free trial. Just go to coderabbit.ai, link will be in the description below. Huge thank you to CodeRabbit for sponsoring this video. Okay, so what we have over here is I've used CMake to generate a solution file for this. I think the first thing I'm going to do is unplug myself from the internet. So in terms of security, obviously this is a fresh install of Windows, and I'm also going to be like re-imaging or reverting to an earlier version of this. Kind of got an image of this like hard drive before I'm running this project. So I guess after this code review, I'll just revert back to that image and then we should be okay. And when, you know, I've cut off internet, I'm not logged in anywhere, nothing here. I've got no personal files here. So hopefully this is going to be safe because, you know, as we know, we should be taking precautions here. Okay. So I'm just going to assume I'm going to be able to hit Control-Shift-B and this will just build. This is my favorite part of the code review videos, by the way, just the suspense of like, will it build? Will it not build? I don't know. Will my computer be infected with a virus as well? I don't know. So many possibilities. Oh, it's trying to download stuff. Okay, back to the internet we go. All right, failed to open file. Ruby build release shaders. Okay, this is probably going to become one of those videos where it's like how to fix a project that you found on the internet. All right, so build is the directory I created, right? So that I could run CMake inside of a generate all the files there. So I know it's a generated directory. Now, failed to open file, and it's this thing. This looks like a shader. It looks like a closest hit shader. It's got a weird .ruby extension on it. So we're going to have a look at what that is. But because we need to somehow get our shaders compiled in Vulkan, Vulkan doesn't actually have any like functions that can compile shaders as part of it. You instead need to use an actual shader compiler. A common way of doing that is to invoke it as a build step. So I'm assuming that's what's happening here. Now, the other interesting thing though is that it's in the release directory, but I could have sworn, yes, I am in fact building debug. So why is that like that? So the first thing that I'm going to do is I'm just going to go into the property pages here and I'm going to go to like build events. Okay. And we can see we've got some custom stuff here. So let's have a look at what this is trying to do. So it's trying to invoke glslang, which is an execute, it's a binary, glslang.exe, which is going to basically take this text file and compile it into this binary file into SPIR-V with the target environment of Vulkan 1.3. So this happens for a number of different shaders. It looks like 3 different shaders. In fact, assuming that these paths are correct, so it looks like in Ruby export shaders, assuming this path is correct, what we can imagine is happening is that you can see it's trying to go into the release directory, but we're clearly building debug. But why is this a problem? Because like, who cares what directory it's going into? Well, unfortunately, these commands usually don't create folders for you. So if release shaders doesn't exist, but this part of the path does, it's probably just going to error us and tell us it can't actually help us. And the thing is, if you look at this error message, it's saying it failed to open this file, right? So this is actually the output file. So really, if you think about it, what could the only reason be for it failing to open the output file? Oh, well, if the path is like wrong or doesn't exist or whatever, and it can't actually create that file because of some other potential issue. In this case, almost certainly because this directory structure just doesn't exist. So if we have a look at build release shaders and see if that exists. So build release just doesn't exist because we haven't built release, we've built debug. Probably going to keep building debug. So I'll just make a directory called release. By the way, I could obviously just modify this, change it to debug. In case we run release in the future, it's just going to be easier for me to just stick to this. It doesn't matter. It's just a directory to read an eventual file from. Then we're probably going to also need a shaders directory. So let's go ahead and try this again and see if it works. Okay, look, so we got the 3 files here that it's reading. And I'm guessing that probably worked because it's proceeding on and that was a pre-build step. So there you go. As simple as that. Why was that not done for us? I don't know, but you know, code, if this is the only issue though, to be fair with this code base, I think we're actually above average. So let's go ahead and try and run this. I'll set it as the startup project and hit F5 and see what happens. Ah, yes, it wasn't the only error. Okay, let's retry this. And the log also seems to have a bunch of things. So unable to load assets path tracer, but that's not, we outputted it to release/shaders. Okay, what's the working directory here? So let's have a look at, if you go to the property pages, we have debugging, and then we have, okay, build debug. That's the working directory. Since we put our shaders into release, let's change it to build release. And then it looks like we need shaders/this. Oh, look, here's our GLTF files as well. They're here inside this release directory. So something copied them in, I guess. Okay, so yeah, so clearly that just seems wrong. So let's grab this path, and then I'm just gonna search for it in the code base, because that way we'll find where it's coming from. And it looks like it's supposed to, again, be an assets path tracer. And then we also have this mysterious extra shader. So what is this? This is shadow rmiss. It's an additional miss shader, but we have path.rmiss. So we've got this path. Let me have a look at the shader source code quickly and see what they're doing. So yeah, this is the miss shader. So that's a perfectly valid miss shader by the looks of it. Then we've got a raygen shader, which traces a ray. We'll get more into the code review part of this video once we get the project up and running, shall we? And then we've got the closest hit shader, which just sets a color to white. Okay, so this is going to be we're going to get like a white object. I think a cube, right? Judging from this GLTF files. So we're going to get like a white cube. So brace yourselves. This might not be the ray tracing you were expecting. Anyway, let's just nuke this shadow shader, because I don't think we need two miss shaders. And then we have to adjust the path, unfortunately. So shaders/ oh, and they're not even the binary versions. Like they're not even the compiled SPIR-V. Like, there's no way this worked ever. Why do people send me projects that don't even work? I don't understand how there's no way this could have worked on your computer. You know, like how? Alexander, how? All right. We've set the working directory to release, so it should have that GLTF file maybe. And then we've also fixed the shader path. So let's try running this again. And we're going to see, oh, look, it generates them again. Oh, are we running? Okay, create shader module. We get a Vulkan validation error, VK create shader module, end of input reached while decoding an op vector shuffle instruction at word 870. Okay, so this looks like half of our file isn't being loaded or something. It's like halfway through like decoding an instruction and it's just not finding the rest of it. So let's have a look at how this works. So add shader, opens up an input file stream, reads it using these spaces, by the way, man. This is, I'm very not happy with this. This is just very annoying. You should, I don't know, like it's more concise, better. Anyway, I mean, I would have a space there to be fair, but anyway, I've never seen this way of, so we create a vector from the iterator P, I guess going forward. Okay, let's just have a look at if we're reading this file at all. So shader size, okay, so that actually looks correct. Oh, you know what might be happening? Yeah, this isn't being read as a binary file. Maybe this was on Linux or something, or using a different compiler like Clang, where this just worked, but you need to indicate that you want it to be read in as a binary file. Otherwise, it might not work. Wonder if that will fix it. Oh, okay, it did fix it, and we got like a white flash for a bit. That is peculiar. Again, plausible that it worked on Alexander's computer if he was using a different operating system or a different like compiler maybe that had binary as default, or I don't know. I don't really know, but I just know that if you're reading a binary file in C++, or if you're reading a text file, like you want to read it as text in C++, just indicate what you want it to be. I mean, there's no way to indicate it being specifically text file as far as I'm aware, but if it's binary, just put binary there. Okay, well that was pretty lucky, I think. And yeah, I mean, it looks like we're working now with no errors at all. So that's fantastic. We've got IMGUI here, demo window, and then we've just got gray. Now, why is this gray? Let's have a quick look at the shaders actually first. So rmiss is gray. Well, okay, so that's why it's gray. If we have a look at the raygen shader, let's just see what the expected result here is. So basically, we have a view projection matrix and a camera position, it looks like, part of here. We're obviously writing out into an image, and we're generating a bunch of rays over here. Sure, we've got the cam projection times this and the view times this to produce a target. Okay, this seems a bit suspicious to me. Ray origin cam position, min and max look fine. Then we're tracing our rays. Okay, so this is really, the good news is it's really simple, right? So I don't know why we're not seeing anything on the screen, but believe me, we will be shortly. What I'm a little bit suspicious about immediately, because this is actually very similar to what I did in my ray tracing series. In fact, let me bring up that code. I'm gonna have to connect to the internet briefly. Shh. Okay, so over here in my ray tracing series, this is just on GitHub, the Cherno/ray tracing. If we have a look at the renderer, actually, I think it's in the camera. Yes, so camera recalculate ray directions. You can see it has a target and it's the inverse projection multiplied with the 2 coordinates. And then we have the inverse view multiplied with the normalized target divided by target W. So that ultimately gives us our ray directions. So the biggest blunder here seems to be the fact that it needs to be the inverse projection and the inverse view. And that's what I was suspicious about. I guess we also need to do the perspective division, but I don't think that will not show us anything on the screen. So yes, those should definitely be inverse view. This is just fixing someone's ray tracing code is what the series has become. Anyway, okay, so let's have a look at where camera properties is coming in from, and then maybe we'll be able to fix this. And we might as well start our code review of the project. So we have all of these C++ files here. They're not in any directories or anything. I mean, these could just be filters, right? Yeah, they are filters. Okay, good. They are in directories. Looks like the .cc extension is being used instead of like .cpp, which is fine. I think that's like the Google code style guide or something likes to do that. And then .hh or something for the header files, which the header files aren't even here, by the way. So that's a bit annoying. Yeah, .hh, nice. I just use, .h and .cpp, but it's an extension. It's a file name extension. Let's not get too upset over it. So here's what looks like the ray tracing code, and then there's quite a lot of stuff here. So we can get into this in more detail. I'm just going to try and fix this project first, because otherwise there's no point, kind of explaining this code to you guys and doing a code review if it doesn't even work properly. Oh, here it is. Okay, okay, good. So looks like the cam.mat, which I'm guessing is the projection matrix. I don't know why it's called mat. In the shader, it's called projection, but you can see that this struct matches this, right? So it is being set to the inverse projection. So yeah, step 1 in terms of this code review, and like my advice for what you should change, is do not call this projection. It's the inverse projection. Very important. Call it something like this or like that, or I don't know, just make sure that you indicate that it's the inverse projection matrix, because that's very different from the normal projection matrix. And same with view, should be inverse view. Otherwise it is quite different. We seem to be doing like a little times -1 on, okay, so we got like in our matrix, we got this area here. It's a 4x4 matrix. And over here, we seem to be flipping. I wonder what that does on the y-axis. So that might, I don't know that I've ever seen this before, but if I had to hazard a guess as to what that's doing, it's probably just flipping the y coordinate, because Vulkan, it's quite common in Vulkan to want to vertically like flip the image. So maybe that's doing that. But either way, I think a times equals -1 is not going to cause stuff not to render. So yeah, so this looks fine. And yeah, we're not seeing anything. Or actually we are seeing something for a second and then it's gone. Is our camera moving? Can we move our camera? Okay, so we got editor camera.cc over here. Okay, so runtime seems to do position.z minus equals 0.001. Update matrix, recalculates the projection and the view. A view with a lookout matrix with just position. The projection definitely doesn't need to be calculated at every single frame, because I'm guessing runtime runs every frame, right? Main.cc. Oh, this is interesting. So we can use either SDL2 or we can compile with GLFW instead. Interesting. But yeah, this looks like our main loop. This looks a bit messy. Interesting. Okay. And then that's calling camera runtime, and then that's doing begin draw and draw. Okay, so yeah, so this is happening every frame. So projection, unless the field of view, the aspect ratio, so the window like resizing or whatever, or the near and far clipping planes change, you don't need to recalculate this. So I would probably almost split this up to just be like update view or recalculate view and then update projection. Okay, so this is probably something that comes up fairly often, I think, where people just don't know exactly how to approach something like this, because if you're just not seeing anything on the screen, obviously it can get a little bit, I guess, intimidating as to what you're supposed to do next. What I would probably do next, depending on my familiarity with the code base, is I don't like the fact that you can't control the camera. Like, I think that you should be able to control the camera, because that helps with debugging a lot. You can see if it's like just maybe it's somewhere else in the scene where you didn't quite expect, and if you turn around, maybe you'll see it, something like that. We are animating the position of the camera going backwards by like 1,000th of a unit by like, so I guess that's like what, 1 millimeter every frame, which probably explains that white flash, to be honest, because we we know that if something is white, it's the cube. The way this works is if our ray tracing hits something, it's white. And if it misses, it's gray. I like that this was specified as one argument, but this was not specified like this. It was just... Anyway, obviously this code could be wrong. It seems pretty normal. So let me explain this shader a little bit before we start modifying it. So I'm sorry, first of all, that I didn't continue my ray tracing series. I do want to continue it to some extent. I've talked about this before, maybe incorporate it into the Cubed project that I'm doing, which is the building like a C++ game from scratch, because I want that to be like a ray traced game as well. Although maybe it makes sense to just have a little standalone series that is the continuation of the ray tracing series where I show how to actually move all of that stuff to the GPU like I was originally intending to do. But anyway, the way this works is basically there is a command that we run in Vulkan called it's like VK command trace rays or something. If I search for trace rays, we'll find it over here. I don't know why it's wrapped inside this interface thing that gets the actual device block address, so it gets it from the DLL. That's a little bit weird, but anyway, here it is, VK command trace rays, and then when we run this command, it will basically, dependent on our size over here, which is 1280 by 720, it'll kick off that many rays. So for 1280 times 720, which is roughly like what, about 1 million or so, around 1 million instances of this raygen shader, .rgen is how we know it's a raygen shader, they'll be basically kicked off, kind of like a compute shader. We'll just run like 1 million instances of this. And then it's basically up to us to be like, hey, we would like to use this shader to trace a ray. So this math just needs to work out our ray origin and our ray direction. Basically, that's it. That's what it's doing. I mean, of course, there are flags. There are like shader binding tables for like making sure that we land in the right closest hit or miss shader, other complicated stuff that we really don't need to care about here, as well as like the range, right? So Tmin and Tmax, and then there's payload as well because we want to be able to communicate between the shaders. But anyway, the point is we just need to calculate array origin and array direction. So where is our ray? Where is it going? Let me know and I'll trace a ray for you. So basically this happens per pixel. Once it traces a ray, it's going to hit either something, right, that is inside our acceleration structure. That's actually a really important part that I should have elaborated on. So we have this acceleration structure that we take in, that we build in our C++ code, which basically just contains our whole scene, right? So all of like the scene geometry, the transforms, all of that stuff, the hierarchy, I guess, all of that is inside this acceleration structure, so that when we trace a ray, we're either gonna intersect a triangle inside that acceleration structure. Doesn't technically need to be a triangle, but that's besides the point. We're either going to intersect something inside that acceleration structure, or we're going to miss it. And if we miss it, we just wind up inside this miss shader, we run this, and then we basically get back to here, or we're going to hit something. And we might hit multiple things, which is why there's an any hit shader as well, which runs for every single hit. This only runs for the closest hit. You can tell because it says C hit, so I'm expecting it's the closest hit shader. Also, when we created this shader, you can see it was the closest hit shader. So in this project, all it does is it sets this payload, which basically is just something that allows us to communicate between these shaders. It sets the data in here. It's just a vec3. It could be a struct, usually is, but in this simple example, it's just a vec3. It just sets it to white, right? To 111. That's the vec3. If it misses, it instead sets it to 0.2, to like a dark gray color. So then you can see that what we do once we get back from either hitting or missing our single ray that we traced in this instance of the raygen shader that ran for this specific pixel, we write the value into this image. We're just storing it in the image. The coordinate is this launch ID, which we obviously need to know so that we know kind of which pixel we are in the image. And then this is just the color that we're storing, which is gray with an alpha of 0. So that is basically how this whole like GPU side ray tracing, ray trace shaders, all of that work. It is really simple. It's really powerful. The best thing about it really, apart from the fact that it's very, very fast because it's hardware accelerated, is the fact that it does all of the acceleration structure detection for you. You can actually do intersection tests yourself as well inside like a special shader. That's useful for like, you know, volumetric effects. Maybe you want to like trace through a cloud or something and there's like specific things. But if you're just trying to intersect a ray with triangles, which is the most common use case for just rendering geometry, that is done for you, implemented kind of at the driver level, at the hardware level. And because of that is blazing fast, which is amazing. So now that we kind of know how this works, we can see why it might be beneficial for us to actually visualize these ray directions. Because if we just look at them instead of either white or gray, we'll see per pixel where that vector is supposed to be going. So we should see like a nice gradient where stuff on the right is going to be like more red, stuff up should be green, because first of all, these are normalized. So they're always going to be like a unit vector, but also we're in this kind of -1 to 1 space. And this is in fact kind of like a 2D coordinate as well. The blue should be basically non-existent. I think we'll be going -1 for blue anyway. So as long as the camera is in fact in the right place and it's facing forward into -1 space, we shouldn't see any blue. And this should be a pretty good visualization of whether or not that part is working, which of course involves all the camera matrices and stuff like that. Okay, cool. So that does actually look pretty good. So we got our green, we've got both kind of over here. We got red, we got black. So it does seem pretty reasonable. So now we have to think about what next to do. So I think that at this point, I really want to actually be able to move the camera around. Now, I'm not going to add in a whole like input system. That would be the best thing to have, like some kind of WASD, you know, fly around camera or whatever. That would be great. But I think we can at the very least just be able to manipulate this position variable using IMGUI. So let's have a look at where IMGUI is actually being rendered. Okay, so over here we have a debug UI function inside render.data.cc, and you can see that's where it's showing the demo window. Now, unfortunately, the way that this author has kind of made this happen is we do both the new frame, the actual IMGUI stuff, and the rendering of that IMGUI stuff within this one function, which means there's no way externally for us, at least as far as this API supports, to kind of inject our own IMGUI debug stuff. Like it basically has to be inside this class, which is a little bit annoying. It would be better for us to be able to basically have a function here, maybe that's called inside like the client side, like main.cc code or whatever, that lets us actually specify what we would like to do rather than just debug UI and that's it. However, what I'm going to do, you know, this is just a debug test anyway, not the best design, but I'm just going to shove camera in here. So camera is what exactly? It's a RB shared, just a shared pointer. Okay, I don't know why. This is another thing that I'm not the biggest fan of when people start making their own types out of existing types. Just use the existing type. Like that is just way more clear. You don't have to worry about all this stuff and including this and whatever else. But we'll just grab this shared pointer and then into debug UI, we'll have our camera, and then I will add that obviously to the header file as well. Probably need to include this stuff. So source renderer editor camera. So backer directory renderer editor camera. So let's do renderer editor camera. See if that compiles. See, this is what I mean. Shared is not a member of RB. It's probably wouldn't have happened if you just had, I mean, obviously you need to include memory or whatever for that as well, but it just makes it a little bit nicer. Okay. So what do we need to do? We just need to include Vulkan helper. Okay. So it's in the same directory, I think. Helper.hh. Build this. Okay, cool. So there we go. Now back in render data, the reason why we did this is because let's not show this demo window. Let's instead do IMGUI begin. We'll call this camera, and then I'll just do IMGUI drag float 3. We'll say position. Now we'll need a GLM value pointer of camera. So the camera position is private. So I'm just going to make this public because we're debugging. So camera.position with a dot. Actually, it's a shared pointer. We're going to have to also include GLM GTC type pointer in order to get the value pointer function. And I also want to make the increment like really quite small. That way, like our scene's not huge, I'm expecting. I actually don't really know how big the cube is and everything, but we'll see. Okay, so now we have a way to adjust the position, but what is also happening is, remember, we're animating the position every frame. So I don't really want to do that anymore. Let's comment this out and let's just run this and see if we get that IMGUI kind of UI that we can use to control our camera. Okay, we also need to get the shader back to being hit value HV. All right, so here it is. So 002 is where we start off with. Oh, so see, this is what I mean. Like we can now easily kind of see this for values less than 1. In fact, at exactly, oh, look at what happens at exactly 1. Anyway, for values less than 1, we just see the cube. And in fact, going negative as well, probably up to -1, yeah? Yeah, we just see the cube. Otherwise, we don't. Yeah, this is quite weird. So there's a few directions we could take here. See what I did there? One of them is the ray direction is probably wrong, even though we visualized it. I wonder if we can visualize it with the camera moving and whether or not that will maybe give us a different result. No, not really. So this doesn't make sense. The fact that this is not moving at all doesn't make sense, because if you think about it, the ray direction is based off of the camera view. So I'm changing this value when I'm changing this, but nothing's changing here. So that's very suspicious. It kind of seems like our camera view is just not getting to the shader. That'd probably be my first guess, but it seems like it does. Camera get view, we invert it, and then it's in the second location here. So that's very weird. So the next thing, I mean, that's very suspicious. But the other thing that I am interested in seeing at this point is if we go back to, let's go back to that hit value. And then I want to have a look at, so we think that at 1, basically, I would like to have a look at this acceleration structure. The best way for us to actually just make sure that the geometry part of things is working is by using an external tool like Nsight. So Nsight Graphics, I'll have a link to this in the description below. Basically, it's just a graphics debugger. This one is by NVIDIA. It works with NVIDIA GPUs. You can use RenderDoc. I don't know to what extent that supports all the ray tracing stuff, but let's set up our application executable to be ruby.exe from debug, obviously. And then the release directory will be the working directory. And then I'm just going to launch the graphics debugger here. We get some errors here that might be because of the stuff that's being injected, but we'll just capture this and then we'll hit start graphics debugger, terminate. Okay. I have kind of talked about graphics debugging in the past, probably in some videos, so I'm not going to spend too much time on this. This video is getting long, but basically this just lets us see all the Vulkan commands that are running as well as inspect them. So here's command trace rays. You can see it's got the raygen hit miss shaders, and then we've got this context as well that we can look at. So inside here, so let's say raygen, you can see we've got acceleration structures, and then here is the acceleration structure. So if I click on this and then we have an open in ray tracing inspector, then I can have a look at the geometry and look at that. Looks like we see something that resembles, yep, a cube. Check it out. So we've got a seemingly normal cube inside our acceleration structure. That's really nice. So if we come over here, oh yeah, over here we can also see the transform. So you can see it's just an identity transform, normal. So that's important to just note that you haven't messed up your transform. It looks fine. And then I think we should also be able to see the actual vertex data. So in triangles, we have the vertex data and the index data. If we have a look at the vertex data, you can see that it is in fact kind of like a unit cube. It's not really, it's a 2 by 2 meter cube, but close enough, you know, from -1 to 1, a 2 meter cube, which explains a little bit about, like, remember we saw it at z equals -1 and at z1. So those are like the two kind of edges. So we see the edges, but we can't see anything further than that, which kind of might be like a clipping issue, like a near clip, far clip issue, even though I think ours was set correctly. So that's a bit strange. And our index data is obviously correct as well. I mean, the fact that we see this here tells us that index data and vertex data are in fact working. Otherwise the geometry here would be messed up. However, we didn't really know the scale of it. So this tells us the scale. It's a 2 by 2 meter cube. And I am saying meter, but obviously it's like a 2 by 2 unit cube because we don't know what units are being used here. It's up to the application, I guess, to kind of add meaning to that. It's just 2 by 2, this cube. That's it. Meters, centimeters, inches, who knows? Hopefully not inches. Okay, so the next thing I'm interested in looking at is, remember that view matrix seemed suspicious. So let's have a look at what the view matrix actually is, because that's another thing we can do. If we go back to the raygen shader, you can see we've got our buffers and we've got this cam buffer. So if we have a look at the cam buffer, we can see our projection and view. Now they both seem to have data, but hang on a minute. They both have exactly the same data. I mean, almost exactly the same data. Look, this is not negative, but this is. Because we did that flip in that coordinate. Oh, they're both the projection matrix. They're both the projection matrix. It's just, this just doesn't have the flip. We only did the -1 flip after we retrieved it from the camera. Does that just mean that the camera is returning the wrong matrix? Hang on a minute. Let's go back here for a second. Yeah, so you can see we get projection, then we do the flip. So the view doesn't have the flip. So what's the camera get view? Oh my goodness me. Are you joking? They're both returning projection. I'm just gonna dig up that email. An honest attempt. I don't think there's anything honest about this. Like, how this did not work for you, man. This did not work. This cannot work. Let's try this. See what happens. Okay, we kind of get our cube, but it's, first of all, it's at a bit of a weird angle, and second of all, the aspect ratio is doomed. Let's have a quick look at the, so there's more is the point. Editor camera, right, creates the, so we've got position, we've got rotation. Okay, we've got 3 constructors here. So yaw and pitch is just not set in these constructors for some reason. Is it used? Yeah, it's used to get orientation. Is that just uninitialized? Yeah, yaw and pitch. Wait, does that make it to be like, is it still uninitialized when we ask for it? Okay, this is why you always just initialize it here, man. just initialize it here. Because if you initialize it here, you don't have to forget. You don't get to forget to do it later in a constructor. You know, when you add like 5 of them, you just do it here and it's done. Like no problem, done. But that doesn't explain the aspect ratio. That explains the weird orientation, perhaps. So now these are 0, which is good. Yeah, okay, so now we're looking front on, but the aspect ratio is weird. So that's almost definitely, we know it's a 2x2 meter, I'll say, cube here. So it's definitely the projection matrix. So let's have a look at the projection matrix. Perspective radians of aspect. How's aspect calculated? Static cast flow, W width divided by height, and they're both units. Okay, so what you're doing is, yes, you are correctly kind of casting to a float here, but you're actually dividing 2 integers together. This is a uint. This is a uint. So I'm expecting this gives you the aspect ratio of 1 because they both get kind of, well, let's just have a look. So this is 1280, this is 720. And what's our aspect ratio? Yeah, it's 1.0. So what you need to do is basically make sure that at least one of these guys is cast to a float probably before you do anything. I mean, I usually end up doing both of them. It doesn't actually, I don't think you actually have to. In fact, you don't actually have to, but it just, in my opinion, it kind of looks a bit more cleaner and telling almost in a way. I don't know, man. I just do it that way. But at least I do it correctly. You know, there's our aspect ratio. Let's have a look. Do we see our cube? We see our cube. And we can actually start to see it from different angles as well. So we can verify that it is in fact a 3D cube. That's not too bad. I mean, the uninitialized variables are annoying. This is annoying, but the fact that getView just used to return projection and this was sent in for a code review as an honest attempt, no, I'm done.